So we just talked about a charging capacitor. Now we're going to talk about a discharging capacitor. Now what did I do? Well, here's how I did this. I'm going to draw this really light. I had a battery, I had a resistor, I had a capacitor. Well, let's make this dark. Here's my resistor, here's a capacitor, and what I did was I used this battery to charge the capacitor up, okay, to its maximum. And then what I did is I have a wire like this, and I have a switch kind of a thing. And what I'm going to do is I'm going to switch it down to, so at t equals 0, this is fully charged. At t equals 0, Q equals Q max. Now the maximum charge, by the way, here, right, is going to be CE. If you started from, if this was E and this is C right here, this maximum charge is C times E. But sometimes they just give you a problem where they tell you what the maximum charge was. So you can figure out what E was, but you don't need it. So then I'm going to, at t equals 0, I'm going to go boom, like this. And so that means that I can just not even think about the battery anymore. It's just been shorted out of the circuit, okay? Okay, now so remember what we had when I did have that battery in there. I had E minus IR, right, minus Q over C equals 0. Well, now what I've done is I've just kind of erased the battery out of it. It's gone. Because now when voltage man goes around this loop, there's no more battery in there. All we've got are these guys. Well, now I got to do is solve the differential equation for this, because and see what happens. Okay, so let's divide by R again. So we get minus I minus Q over RC. And then equals 0. So let's put this on the other side. Well, put the I on the other side. So I is equal to negative Q over RC. And this I is dQ dt is equal to negative Q over RC. Okay, and then now let's switch these guys around. So we have dQ over Q equals negative dt over RC. And now I'm going to integrate both sides. Now this is going to be at time t equals 0. Now at t equals 0, what do we have? We had, I'm just going to call it capital Q. That was our maximum charge. Okay, to some value of Q at some time t. Well, if you do this, you get the natural log of Q over Q. And when I do this, I get negative T over RC. And then I raise to the power of E, both sides to the power of E. And I get Q over the max Q equals e to the negative T over RC. Multiply both sides by the maximum charge, our starting charge. And you get Q equals the maximum charge times e to the negative T over RC. So there's my equation for charge as a function of time. Now, does it make sense? Always check your equations and see if they make sense. Okay, now at t equals 0, what was my maximum charge? It was Q. Look, and t equals 0, this becomes e to the 1, or e to the 0 power, which is 1. Okay, and you got it. Makes sense. Now, if you wait a long, long time, what happens to the charge on the capacitor? I mean, think about it. At t equals 0, this has got all kinds of positive charge here and all kinds of negative charge. If you close this switch, what does this positive charge want to do? It wants to rush through the circuit and cancel out all those negative charges there and have 0 net charge on any plate. It wants the plates want to be electrically neutral. They hate all this charge separation. And that's exactly what happens as the charge goes to, as time goes to infinity, the charge goes to 0. Yay. Now what about the current? The current. Well, what we're going to do here is take the derivative and see if it makes sense. So let's figure out the current. Current I is dq dt. So that means I got to take the derivative of this guy, which I'll just do. You got the maximum charge Q. Now you got to take the derivative of the inside part, which is negative 1 over RC. And then take the derivative, and it's negative T over RC. And so what we've got here, I, is equal to Q, negative Q over RC, times e to the negative T over RC. Dimensionally, does this make sense? Yes, this is charge per unit time. Okay, now it's negative. It's negative. What does that mean? It means that the current, look what we started my analysis, and let me zoom all the way out so you can see the whole thing. And I'm trying to get this done. I got 3 minutes left. What did we assume here? We assumed that there was a voltage drop going like this, right? And then we had a voltage drop across this, right? Well, when I get a negative current, what does that mean? It's actually going in the opposite direction that I said when I wrote my voltage equation. And that makes sense, because what direction is the current going to be when you discharge the capacitor? It's going to be this way, not this way. I assumed it was going this way when I wrote this voltage equation right here. But it's not. It's going the other way, and that came out in the math. Woohoo! It told us the current is going the opposite direction. That's a good thing. All right. Now, let's draw the equations for this. I'm sorry, let's draw the graphs. Q over T, and then below it, I over T. Now, Q, down here, starts at its maximum. T equals 0, it's Q. And then it goes down like this, and it approaches 0. And here's our little tau guy right here. But take the derivative of this. Look at the slope. It's negative, but it's maximum negative over here. Now, what is Q over RC? That's our maximum possible current in a discharging capacitor. And then it's just going to go like this. And there's our tau again. Okay? And so this is Q over RC. These equations for charging and discharging capacitors, and their graphs for charge and current, guaranteed you're going to see them on the AP test, especially on the multiple choice. But because it's very easy just to give you a big set of graphs and say which graph best represents the discharging capacitor. But it really does make sense. Okay, and so study it. It's very interesting. And exponential equations are a great thing to understand. A great little piece of mathematics for you to understand, because it helps you in all kinds of ways. All right, that's it for today.